Friends, we will be discussing the fourth module of the electric circuit analysis subject, which pertains to Laplace transformation and its applications to electric circuit theory. In particular, what we will be seeing is some fundamentals of Laplace transformation and properties, and eventually we will see how we can apply these properties to circuit analysis and make our analysis simpler than what you have seen till now. At the end of this chapter, you will be able to solve circuit problems which are pertaining to linear circuits. By that we mean you will have voltage sources independent, current sources which are independent, and probably even dependent current and voltage sources. The passive circuit elements will involve the resistance, the inductance and the capacitance. So, generally these are what will constitute the circuit elements in our consideration for this subject as we proceed now. The advantages of using the Laplace transform method is that unlike in the case of solving circuit problems with differential equations, where we have to use the method of solving the method of differential equations with obtaining the complementary function and the particular integral after substituting the initial conditions. In the method of Laplace transform, what happens is we will get the complete solution in one stroke. So, that is a very big advantage. There are other advantages also. I suggest that you will be able to appreciate them by the time you see the different applications of Laplace transform. By that time you will be able to appreciate what the advantages of the method of Laplace transform are. Now, let us begin with defining what is a Laplace transform. For that, let us consider a signal which are typically functions. Now, if I have a function, I will call it as f. It goes from infinity 0 to infinity, which means it takes non-negative values. It could be a function of time. Time we usually consider as starting from 0. That need not be. 0 is only a reference for us. Now, we have signals or functions which are taking values which are positive, non-negative, and they can go between minus infinity and infinity. Now, for such functions, we say given a function like this, we define its Laplace transform as integral 0 to infinity e to the power of minus st f of t dt, and this is denoted by a symbol corresponding to this f. We call it f of s. Corresponding to f, we take the capital letter f of s. This s is where s is a variable which takes complex values. There is another way of writing s belongs to the set of complex numbers. So, what you are doing here essentially is you are taking a function which is probably a function of time, that is a real variable, and then through this transformation which is defined through this integral, we are getting into the domain of complex numbers. Now, if you will see here, we are writing this object e to the power of minus st. Now, we must understand the physical implications of this. Whenever you write an object e to the power of x, you can ask what is the dimension of this object or this variable x. Let us write e to the power of x in the expanded form, which is 1 plus x squared by 2 factorial plus x cube by 3 factorial and so on. So, that is an infinite series. Now, what I want to tell you here is that this x here in e to the power of x which must be dimensionless. That is because, let us say you take a dimension for this. If you take the dimension for x as length, then this will be length, whereas this is going to be the square of length and this is going to be the cube of length, and that addition is meaningless. Therefore, this whether it is length or any other unit or any other dimension, it cannot be valid. Therefore, what we are going to do here is we are going to by force take this x to be dimensionless. Now, in this case, in the place of x you have e to the power of minus st, for that exponent is st. Now, if you say that t is time and st must be dimensionless, which implies s must have the unit, s time must dimension 1 over time. If s has dimension 1 over time, then what we say is that s has the dimension of frequency, because you know that the dimension of 1 over time is frequency. Therefore, we say s is frequency, and since s is a complex number, as we have taken from here, we call s is a complex frequency. So, what we are doing here in essence is, let us come back to this equation, let us call this 1. What we are doing here is, we are transforming this function which is in time domain, if you consider t as time, into the complex frequency domain, all right. So, that is the transformation from the time domain, and time is a real variable, real domain. We are transforming it into the complex frequency domain. So, this is the Laplace transformation that we are talking of. Okay. Now, let us understand this. Now, when we do this, we are transforming all signals into a different domain. The idea is, it is easier for us to solve problems in this domain rather than in this domain. Our problems are stated in the time domain, whereas we will transform the problem into the complex frequency domain. There it is easier for us to get the solution, and once we get the solution in that domain, we will be able to come back to the time domain, which is where we want our solution to be. That we will do by what is called as the inverse Laplace transformation. All right. Now, there is a way in which we are going to denote this. The Laplace transform of this statement 1, we are going to write it in a different form. The Laplace transform of f of t equal to f of s. So, this will be our notation. Okay. You read this as Laplace transform of f of t equal to f of s. Okay. That is the same as the statement in 1. Now, let us see what are the properties of this Laplace transform. We will combine 1 or 2 properties directly. Now, let us say L of f1 of t equal to f1 of s, and L of f2 of t equal to f2 of s. What it means is, given this, then we have L of, let us do this, f1 plus, let us say I have a constant f1 of t plus c times f2 of t. This is called the linear combination of these two functions, f1 of t and f2 of t, such that f1 and f2 satisfies this. Now, if we do this, then what we get, we will apply this. Here we can set, let f of t equal to f1 of t plus c times f2 of t. Now, I said here c can be a constant, here c can be real or complex. It does not matter whether c is real or complex, we get the same result. All right. Now, with this, let us get back to this. Now, this is L of, that is L of f of t, and that turns out to be, let us go back and apply this using 1. I get 0 to infinity e to the power of minus st f1 of t plus c times f2 of t dt. Now, I am going to split this into two integrals, that is the same as integral 0 to infinity e to the power of minus st f1 of t dt plus, I am going to skip one step and I am going to take c outside, c integral 0 to infinity e to the power of minus st f2 of t dt. And you know that this object on the left hand side, the first term on the left hand side must be the same as f1 of s, which is coming from here, and the second object must be plus c times f2 of s. So, the result that we have got now is that if I have a linear combination of several functions, then I will get equivalently after transformation the linear combination, the same linear combination of the corresponding Laplace transform. This is the same as telling that the Laplace transform is a linear transformation. Okay. So, here we now have this result which says this must be f1s plus c times f2s, which is the result that you have derived here now. So, this is a useful result. This is not valid only for two of them, this is valid for any number of them. So, this is the second property that you are going to be. Right, this is the linearity property. Now, let us take the Laplace transform of certain simple functions. You have seen what is called as the step Laplace transform of, let us say, useful functions. You have seen, for instance, in several applications the unit step. So, the unit step we will call it u of t. You can say that is equal to 1 for t greater than or equal to 0, that is equal to 0 for t less than 0. There is a way of graphically representing this, and that is the following. This is t, and here I am going to call this 0. Please understand, I could have defined this in two ways. I could have made it 1 for t greater than 0 and 0 for t less than or equal to 0. There are two options. Now, by this option, I am making the value at t equal to 0 equal to 1, which means here I am going to write this dot and make this to the left of 0, it is 0. When I write the dot here, this is 1 and this is u of t. When I write the dot here, what it means is at 0, it attains the value 0. All right. Now, I could define it in another way. We usually use the one that I have shown you now. That could be defining it like this. It is u of t is equal to 1 for t greater than 0 and it is equal to 0 for t less than or equal to 0, which means in this case the unit step function attains the value 0 for t equal to 0. Then we do not put the dot there, we are going to put the dot here. So, even graphically we are able to distinguish between one and the other. So, we will stick to this t greater than or equal to 0, it is 1 and it is 0 for t less than 0, which means our graphical representation as I did before is going to be this is 0. Please observe that I put the dot there. Now, what we are going to do now is we are going to get the Laplace transform of this function. By our notation, if I had u of t, which is the lowercase letter, I am going to have the uppercase corresponding, which is u of s. So, let us do this. Laplace transform of u of t, we are going to denote it by u of s, the uppercase corresponding to this lowercase, and that is the same as integral 0 to infinity e to the power of minus st u of t dt. Now, what you see here is that u of t is 1 for t greater than or equal to 0, and here it says the limits of t are 0 and infinity, and in that range, in that domain, u of t is equal to 1. Therefore, this turns out to be integral 0 to infinity e to the power of minus st 1 dt. Let us evaluate this, that is e to the power of minus st divided by minus s going from 0 to infinity, t going from 0 to infinity, and in the upper limit it is minus 1 over s. When t goes to infinity, we are going to take this to be taking this to be 0. That is a condition that we will come to depending on what is the real value of s that we are going to take here. So, it turns out to be 0 because I am going to take t to be minus infinity, and when t goes to 0 it becomes minus 1. So, that is the same as u of s equal to L of u of t, which is 1 by s. So, this is a very important result for us. All right. Now, let us look at other functions, and let us see what are all the other properties that we can get. Now, if I want to ask what is the Laplace transform of a sinusoid or of a cosine, then I am going to do this. Let us take another property. If Laplace transform of f of t equal to f of s, what we want to find is Laplace transform of e to the power of a t f of t. That is our problem now. All right. Now, let us do this. Laplace transform of e to the power of a t f of t is simply the integral in 0 to infinity e to the power of minus st into e to the power of a t f of t dt. Instead of f of t, I am now writing e to the power of a t f of t because I want to compute the Laplace transform of that. Now, I will combine these two exponents, and then I am going to write this as integral 0 to infinity e to the power of minus s minus a t f of t dt. Now, we will observe that in our definition of Laplace transform, we had s here. Now, instead of s, you have s minus a. So, it is straightforward that you can replace, if this were to be s, the right hand, the expression here would have been f of s. This is f of s minus a. Therefore, this turns out to be f of s minus a. Therefore, what the result that we have is then once you multiply this by an exponent, then it will give you a translation in the translation means shift in the frequency domain. So, this turns out to be f of s minus a. So, that is an important property for us. Now, using this property, let us see how we can easily compute the Laplace transform of sin omega t. What is this? At the same time, I want to ask what is the Laplace transform of cos omega t, because these are signals that we use quite frequently, the sines and the cosines. All right. Now, we will use this and we will use that property also. Now, what I am going to do is we are going to use the Euler's formula which says that e to the power of j omega t is cos omega t plus j sin omega t. We are all familiar with this. I am going to use this. So, what I am going to do here in particular is instead of a there, I am going to use this j omega. All right. So, let us use that. What will that tell you? By this property, e to the power of Laplace transform of e to the power of j omega t u of t. All right. That will give me, I know what what is the Laplace transform of u of t, that is u of s, which is 1 over s. Now, instead of a, I have j omega t. So, therefore, this turns out to be 1 over s minus j omega, because instead of a f of s minus a, Now, A is this j omega, therefore, I get S minus A, therefore, I get S minus j omega. Now, I am going to write this as S plus j omega divided by S minus j omega into S plus j omega, because I am rationalizing now. And once I rationalize, I am going to get this as S plus j omega divided by S square plus omega squared. S plus j omega into S minus j omega will give you S squared plus omega squared. Now, let us take a look at the left hand side once again. The left hand side is this, which is Laplace transform of u of t is 1 for t greater than or equal to 0. Therefore, I can write this as just 1. So, it is the Laplace transform of e to the power of j omega t, which is the same as Laplace transform of, we will use the Euler's formula, cos omega t plus j times sin omega t. Now, we know that Laplace transform is a linear transformation. Therefore, this is one function multiplied by this constant, second function, the two are added. Therefore, I can write this as Laplace transform of cos omega t plus j times Laplace transform of sin omega t. Now, what this says is, now we have come from here to here, these two must be the same, or if you look at the right hand side here, this turns out to be S divided by S squared plus omega squared plus j times omega divided by S squared plus S squared plus omega squared. Now, what we are going to observe here is, this is a real part, this is a real part, this is an imaginary part, this is an imaginary part. Now, since these two must be the same because of the derivation that we have did, this must be the same as this. I have taken this from the left hand side, I have come to this, from the right hand side, I have come to this. Therefore, I have this which is the real part, this which is the imaginary part. On the right hand side, this is the real part, this is the imaginary part. So, if I equate the real and the imaginary parts, the result that I am going to get is the following. I will put this as equal to this. So, I get Laplace transform of cos omega t should be this, which is the real part, that is S divided by S squared plus omega squared, and Laplace transform of sin omega t. Please observe that j is here, the same constant j is also there. Therefore, the Laplace transform of sin omega t must be equal to omega divided by S squared plus omega squared. So, these are other two important results that we have. So, what is it that we have seen till now? We have seen the definition of Laplace transformation. We have seen the property of Laplace transformation as a linear transformation. Then we have derived the Laplace transform of the very useful function, which is a unit step function. Then we have seen that if I exponentiate this function, which means if I multiply the function by an exponent e to the power of a t, then it will be a shift here, because S is now being shifted to S minus a in the complex frequency domain. I get this property. Now, using this and this, I am able to obtain very simply the formulas for the Laplace transform of cos omega t and the Laplace transform of sin omega t. All right. So, these are the important things which you must keep in mind. What we will do next is define a it's not a function, it's not a function. We will define an object which is called as the unit impulse, because this is used very frequently. The unit impulse is a peculiar object. Unlike several functions that you might have seen, there is a very wide misconception about the unit impulse. I want to give you what is correct here. The unit impulse is not defined as it is There are people who will define this unit impulse. It is denoted by delta t, infinity t equal to 0, this 0 t not equal to 0. Now, this definition of the impulse is wrong. You will find this in several places, but please observe that this definition is wrong, and it has to be defined only through what is called as an integral. So, define only through an integral. So, please keep this in mind. Now, let us see how this is defined through an integral. Delta of t, if you let me take a function f of t and then I multiply by delta of t, and I said it is defined only through the integral. Now, if I take this integral t going from minus infinity to infinity and integrate this with respect to t, what I am going to get is I am going to get the value of this function at t equal to 0. So, I will get f of t at t equal to 0, that is f of 0. So, this is how I am going to define an integral. Define the delta function, the unit impulse. The unit impulse should not be defined like this. Please bear in mind. If it is defined like this, you cannot get this integral value as this, because it is graphically represented like this, which is only a pictorial way of representing just because it is pictorially represented like this, there is a misconception that at t equal to 0 it is infinite. It is not the case. If at t equal to 0 it is infinite, you will not get this result. Now, I will tell you how you can arrive at something which is like this, which is an impulse function, unit impulse through approximations. Now, let me take this function which I am going to call delta epsilon. Okay. This delta epsilon is defined like this of t. It is defined as 1 over epsilon for t, okay, for 0 less than or equal to t less than or equal to epsilon, which means if I take this as the t axis, this is epsilon, a small number, let us say, then the height of that is delta epsilon of t. The height of that is, it is constant, this is 1 by epsilon. So, please observe what I have done here. I have said that it is 1 by epsilon for t in the interval 0 epsilon. In the interval 0 epsilon, I have taken that as 1 by epsilon, and it is 0 otherwise. It means everywhere else it is 0. Now, the idea is what I am going to do is, on this I am going to let epsilon become smaller and smaller. Please observe what is this area. This is a rectangle of width epsilon, of height 1 over epsilon, therefore, this area is 1. Now, what I am going to do is, I am going to shrink this epsilon to 0. If this is 0, if I shrink this epsilon to 0, then in the limit what is happening, even if I make this half, this will become double, therefore, this area is going to remain independent of epsilon, as long as epsilon does not become 0, all right. Therefore, what I am going to take is, take limit epsilon tending to 0, there is a caution that I have to give here, I will come to that. Take limit epsilon tending to 0, delta epsilon of t. Now, the caution here is epsilon should not be equal to 0. Please observe, if you make epsilon equal to 0 in the limit, or epsilon actually equal to 0, then you are getting 1 by 0, and division by 0 is not permissible, not admissible. Therefore, you will not let epsilon go to 0. Now, what happens when you do this is, it becomes what is called as delta of t. So, that is what we are doing here. We are letting epsilon go to 0, which means if I take half of this, if I were to take half of this, the height here would become twice. And again this area is still 1. All right. So, this is one way of realizing what is called as the unit impulse function. And in fact, this is not the only way of doing it. We could have done it in a different way. Let me just give you another example to show what it could also be. Okay, this is, let me consider a second example. I will call this as 1 over 2 epsilon. Okay. I am going to make that as the height, but then I am going to take it on both sides of 0. I will make it for minus epsilon less than or equal to t less than or equal to epsilon, and then as before it is 0 else otherwise. Okay, let us take this as the second candidate. Now, let me see what I am doing here graphically. In the interval, you will observe that into interval minus epsilon to epsilon, I have made the width as, I have made it as 1 over 2 epsilon. Okay. What is the width? This width, let us see graphically what it turns out to be. That is the t axis, this is 0, this is epsilon, this is minus epsilon. In t, between minus epsilon and epsilon, it is taking a value 1 over 2 epsilon. So, this value is, this height is 1 by 2 epsilon. So, what you will observe here is, here you have a rectangle of width 2 epsilon, the height is 1 over 2 epsilon, therefore, this area still continues to be 1. This is what, now this is the second candidate, if you want to call it as I have defined here, that is this delta epsilon of t. Now, even in this case, you will see that if I make epsilon go to 0, do not allow epsilon to become actually equal to 0, then this becomes smaller and smaller, whereas the height of this keeps on increasing. You will see that this area is independent of epsilon. Therefore, even this, when you integrate from minus infinity to infinity, because here it is 0, outside this it is 0. So, you will see that if you integrate this minus infinity to infinity, delta epsilon of t dt, what I am going to do is, I am going to take the limit as epsilon goes to 0, with the caution that I will not allow epsilon actually to become equal to 0. Now, you will see that this becomes equal to 1. Now, the idea of getting this definition for this is, if I have a function, f of t, which could be going like this, and let us say at t equal to t naught. I am shifting this, I can shift this function delta of t to t naught, and then I am going to call it delta of t minus t naught. The unit impulse is shifted to t naught. That means, here I will have a unit function, which means instead of having this rectangle here, I am going to have that rectangle here. Now, what happens is, if I shrink this rectangle, and if I ask what is the area that I am going to get when I shrink this rectangle, now this is the area that I am going to get. I will shrink this rectangle more and more. The contribution of this rectangle becomes 1, whereas it will pick up the value of the function at this point. So, this is f of t naught. So, in this case, I can now give what is the generalized definition, which is, if I have this as t minus t naught, then instead of picking the value at f equal to at t equal to 0, it picks the value at t equal to t naught, and then you get f of t naught. So, this is the definition for the unit impulse. It is defined only through the integral. Without the integral, there is no point in defining this function. Now, you saw that there are several examples which will give you this property. We saw one rectangle with the base, with the width of the base being epsilon. You saw another example with the width of the base being 2 epsilon. Both of them will give you the same result. Therefore, it is not only one type of object, which is this unit impulse, which will give you this. There are several things, not just 2, you can have several of them, all of them will give the same result. Therefore, this is not one, there are several of them, all of them give the same result, means they are equivalent in some sense. They are not the same but they give the same result. Therefore, they are called equivalent in that sense. And objects like this, which if you call this as a function, then it takes a function like this and it returns what is called as a number, because this you will see is not a function, this is the value of f at t equal to t naught. Okay. It is taking a function and giving a value. Such objects are called functionals. So, this becomes an because they are equivalent, several of them are there. So, it becomes an equivalence class of what are called as functionals. So, the impulse is defined only through the integral, and it forms an equivalent class of functionals. So, never operate on this impulse or the unit impulse or even a scaled impulse without taking it through an integral. All right. So, please keep that in mind. Now, having defined the impulse like this, the physical interpretation for this is what is important. What is the physical interpretation of an impulse? In this context, there are several physical interpretations. For our sake, we will look at the interpretation through this integral. Now, if I have a function like this, which is f of t, and if I have an impulse here delta, if this is t naught, then this is delta t minus t naught, this is the origin, it is shifted by t naught, it is a shifted impulse, unit impulse. If I have this, then through this function, through this integral, what we are getting is the value of this function at t is equal to t naught. Okay. So, what it means is it picks the value of f of t at t equal to t naught. There are several values for the function, but it takes only that value out of all those values that you have, infinitely many of them. This property is called sifting, not shifting, sifting property. Do not confuse this is shifting, this is shifted, this is called sifting. It picks only that value out of the value of the function here. So, that is one interpretation of this. Now, why do we want this? We will first get the transform of this and then see how this has a relationship to the objects that we have used till now. Which means I want to ask what is the Laplace transform of this. I am going to, this is delta lowercase, capital delta is this. So, we will ask what is this. We will again go to the definition and apply the Laplace transformation. So, that is equal to integral 0 to infinity delta of t e to the power of minus st delta of t dt. Now, you could have seen this, let me recall, delta of t minus t naught f of t dt minus infinity to infinity. This takes the value of the function only at that point t naught. Now, this is the same as delta of t minus 0. This plays the role of f of t here. Therefore, it must take the value e to the power of minus st taken at t equal to 0, because this is t minus 0, that is the same as 1. So, the result that we have is that delta of s equal to 1. Let us put all the results that we have till now. We had u of s equal to 1 by s, delta of s equal to 1, Laplace transform of cos omega t is omega divided is s divided by s squared plus omega squared, and the Laplace transform of sin omega t is omega divided by s squared plus omega squared. So, these are the important results that we have got till now, all right. Now, so far it is looking as if this is a course on mathematics. Now, we will come to some application of electric circuits. For instance, let us say I have a simple inductor. Inductor L, and the current here is I of t, the supply is V of t. We know that the drop across the integer, it must be marked like this, E of t. Now, please do not mark there is a mistake which many students make, therefore, I want to bring this to your attention. If you mark the current like this, now this is L, there are students who will mark this as E of t. Now, if you mark this E of t with arrows on both sides, I do not know which is positive, which is negative. Therefore, I cannot even write whether E of t equal to L dit by dt or minus L dit by dt. I cannot do this. I will tell you why. If this is the case, if I mark the arrow like this, with this as, which means this is positive, this is negative. Since this is positive, this is negative, this must be the same as this. Therefore, I will write this as V of t. So, that is what I get. Whereas, if I mark the arrows like this, if I were to mark the arrow on the other side, then this becomes positive, this becomes negative. You will see that this is V of t, this is positive, this is negative. Whereas, if you mark this as E of t, this is positive, this is negative, then you will get V of t equal to minus L dit by dt. So, in order to be able to write either this or this with certainty, without getting any doubt or ambiguity, you have to mark this only on one side. It is not wrong if you mark it either on this side or on this side, but do not mark the arrowhead on both sides. That is wrong, because I cannot even discern or tell you with certainty whether it is this or this. Okay. So, let us take this example. Now, how do I write E of t in this case? As I have said, the current is flowing like this, and this EMF which is induced in this inductor is opposing the current by Lenz's law. Therefore, I have to take this E of t equal to, this E of t is positive here, V of t is positive here, that must be the same as V of t, that must be L dit by dt. Now, we will come back to our application of Laplace transform. If I were to apply Laplace transform to this equation, then you will get L of E of t on the left hand side, and on the right hand side these two are equal. On the right hand side I get L of L dit by dt. L is a constant, I can take this out, that becomes L Laplace transform of dit by dt. What I know till now is, if you give me an I of t for which the Laplace transform exists, then I can get the Laplace transform of I of t, but I do not know as of now how to get the Laplace transform of dit by dt. So, let us try and do that as an exercise. That is an important property. If I am able to do that, then why do I want to do that? If I am able to do that, then I can transform this equation into the Laplace transform domain, and there I can solve the problem, which is easier than solving this differential equation, or if not in this case, in more complicated cases. So, the exercise that we are going to do now is Laplace transform of the differential of a function. Given L of f of t equal to f of s, find L of d by dt of f of t. So, that is the problem. All that we have to do is simply apply the definition of Laplace transform. We will recall Laplace transform of f of s is integral 0 to infinity e to the power of minus st f of t dt. This is our, by our definition. Now, instead of f of t, you will see that you have d by dt of f of t. Okay. So, that is the only thing. It is a simple exercise. Let us do that now. Laplace transform of d by dt of f of t is integral 0 to infinity e to the power of minus st d by dt of f of t dt. Straightforward. Instead of f of t, I am writing d by dt as f of t. Now, I am going to use integration by parts, first function into integral of the second function and so on. So, what is the first function? I am going to call this as the first function, I am going to call this as the second function. So, it is the first function e to the power of minus st into integral of the second function f of t, all right. Now, this has to be evaluated between t equal to 0 and infinity, that is the first half of the integral, minus integral of the second function. The integral of the differential is the function itself, which is f of t, okay, into differential of the this function. What is the differential of this function? Minus s e to the power of minus st dt. Again, I got to evaluate this between 0 and infinity, all right. Now, let me do this first. Now, there is a minus sign here, I am going to take it. You have s there. Now, what are you left with? Integral 0 to infinity e to the power of minus st f of t dt. We will come to this part. You will see that this is s. What is this now? Go back to this. This is the same as f of s. All right, that is a simpler part. Now, let us come and evaluate the first term on the right hand side. Now, as t goes to infinity, this is f of t into this part will take this to 0. So, the first term here is 0 minus the second term. As t goes to 0, this becomes 1 there, and here t must go to 0, that becomes f of 0, all right. So, we have here that is equal to minus f of 0, or let me write it this way. What is the left hand side? L of d by dt of f of t, that implies L of d by dt of f of t is this, and this I am going to take here minus f 0, all right. So, this is the important result that we have. I wanted to get the Laplace transform of the differential of a function, and this is what I have got. And if this were to be your current, then you can get the Laplace transform s into Laplace transform of the current into this. So, friends, now we have seen the definition of Laplace transform. We have seen, for instance, the properties of Laplace transform. We have seen certain important functions, which is the impulse, and you also have the unit step, and you also have the cosine and the sine. We have seen two more properties by multiplying a Laplace transform with an exponent e to the power of minus at, and then the Laplace transform of the differential of a function. Okay. So, these are the important things that we have seen, and these will be useful in our circuit analysis. Right. Thank you very much.